Hello everyone, this is Mr. 13 Things and I am here in my third of three, I hope, discussions of how to do by basic linear algebra and mathematics and extrude like you do in Inventor. And I left off, the last thing we did in the second video was calculate the normal unit vector. The first thing we did was determine the points that defined your face. So those are defined here. Again, stacked over ones in a column vector format. So the first point being just one on the x-axis, the other one just being one on the y, and one being one on the z. Well, I'm sorry, the first one was one on the z, one on the x, one on the y. We then calculated the normal vector by doing the cross product of the vector that goes from point 0 to point 1 and the vector that goes from point 0 to point 2. We ended up with a unit vector that looks like this. And I am going to now finish. This unit vector turned out to be actually the square root of 3 over 3 mathematically is what it looked like, the square root of 3 over 3, and then I'm extruding 3. So I'm going to take the unit vector, which is the unit normal vector, the unit normal was equal to the square root of 3 over 3i plus the square root of 3 over 3j plus the square root of 3 over 3k. And that might be something you can then go back and prove to students, that the length of this vector is equal to 1. So the magnitude of the unit vector, right, is equal to 1. This is the unit vector, and you do that because the length of the vector, right, so the length is equal to the square root of each of the components squared. The square root of 3 over 3 squared plus the square root of 3 over 3 squared plus the square root of 3 over 3 squared, which is equal to 3 ninths plus 3 ninths plus 3 ninths, right? Square root, which is equal to the square root of 1, which is equal to 1. So it's a useful thing to take students from first dimension to the second dimension to the third dimension, and it's even perhaps more useful to take them to the fourth dimension, where if there was a fourth dimension here, you would still get the magnitude of the vector by the square of the sum, the square root of the sum of the squares of the components. And you can see in the end that's a pretty simple vector calculation, and if I get around to it I'll link you out to that, but it's basically any vector transposed times itself, take the square root of that and you get its magnitude. So it's a pretty straightforward thing, but in the end we ended up knowing that the normal unit vector was this. Let's see if I'm going to erase now. Let me do that. That's not it. I'm going to erase this out, edit, cut. Right, I'll do a little bit more, one more here. Edit, cut. So all we've got to now do is we're going to make our extrude distance 3. So we're going to say the extrude distance is 3. And now all we've got to do is add 3 times this vector, right, to each of our other vectors, and we're done with our basically extrude calculations. So what I'm going to do is I'm going to start with the ones we have, and I'm not going to colorize this because it's getting a little old for me. We're going to start with our first point with 0, 0, 1, and remember the 1 chaser down here. And our second point was 1, 0, 0, and a 1 chaser down here, and 0, 1, 0 with a 1 chaser. And now we're just going to add the square root of 3 to each of these. So this is going to be 1 plus the square root of 3. Right, we're going to add the square root of 3 because we're going to multiply this. We multiply it by 3, right? These all cancel, and we just have the square root of 3. So now we're looking at points. If we add that, it's going to be 1 plus the square root of 3, and 1 plus the square root of 3, and this is 2 plus the square root of 3. Remember, we're adding it to that. And now this is 2 plus the square root of 3, and 1 plus the square root of 3, and 1 plus the square root of 3. And in effect, we now have 1 plus the square root of 3, and 2 plus the square root of 3, and in the end 1 plus the square root of 3. Of course, these are each stacked. So we now have the 6 points that define the extruded shape. And if you now, I will colorize this now. Sorry for it's not sticking with the color. Remember, this was point 0, and this is point 1, and this is point 2. Now, how you want to number these is going to be perhaps become important later, but we're going to kind of go ahead and do it this way. Point 0, 1, and point 1, 1, and point 2, 1. In this, right, we can kind of see where the parentage, if you would, be. And then you can start thinking about the edges, right? We had one edge here and another edge there. You can go in and fill in your edges and go from that, as you might want to now, the next time, extrude something out from something else. Why that wouldn't be important in the end is you might want to know the normals to each of the faces. At this point, you just kind of capitulate to the software, right? You start, from here on, you start letting the students know that it is all abstracted within Inventor, which is abstracted within linear algebra, etc. But when you skip this stuff, these basic calculations, and have students continue up through without going back to some pretty straightforward linear algebra, which they've been using in some way, shape, or form in their gaming systems, 3D space with time, call it 4D space. When you skip that, you without at least introducing students to that, you cause potential problems downstream where people start to believe that really not getting the math or understanding what the math's going on, it can all be abstracted into software without a basic understanding. And you set yourself and everyone else up for problems later when and if those cords are cut. So you can think about this conceptually here, having been done by hand, and if you had thought early on the first original triangles that we worked on, where they were placed, you could think about all the students basically coming to a shape in these new points. So every student, 6 or 8 or 20 or 30 students, could end up coming almost to the same shape or some other shape. So you would have basically legs growing in or legs growing out, how you could think about that. And I'll try to animate that and do some other things here, because in reality you can think about this as well as just doing it the way it was shown here. You could also have thought about it being this unit vector with a time value on each of these new points, and as these base values didn't change with time, these other ones did, and you very quickly get to the fourth dimension, which is growth, if you would. If you want to think about this in 3D, 4D space, you start getting towards the concept of sweeps and quaternions and rotations and flights, and you get effectively to where you're already placing students when you're sticking them in Inventor, and that is, or SketchUp, or SolidWorks, and that is the math of satellites and robots. And the only thing better than satellites and robots are robot satellites. Thanks for listening. We've now been through how to extrude by calculating first the points by using stacked vectors over 1 chasers. You calculated the normal unit vector. Scale that normal to based on your extrude distance, and then add that vector to each point. I just want to point out that the reason you add the ones along the bottom here will come clear later as you start to do basic transformations on this shape to have it fly around or rotate as you start to put things together in parts. So I'm going to think this problem out a little bit more. So in fact, it can be done by groups of 8 students growing in to a common point and coming up with something that's a little bit more real. Basically, we're trying to do Inventor here by hand. We're trying to expose the connections between the silos that exist because of how rapidly all this stuff is occurring. I want to thank Autodesk for making all this possible, and for the innovators in education that will jump in with both feet, even though those of us of our age, this is all wizardry. This did not exist in our heads coming through school. Thanks for listening.